Okay, guys. In the previous class, guys, it was a typo. I was really sick. I told you in the tank of the water, Q in is equal to H over RT. This is, you have to, the right one is Q out is H over RT. Please fix it in your notes. This is Q out, okay? Because I'm teaching from my mind. I have no notes, nothing, okay? I was sick and I'm sick still. The rest is correct. So, in the previous class, I showed you that for the first order system, just recap of what we have done, that RC circuit equals to uh, dynamically a spring and damper, right? And this is equals to the tank of the water that we got. You have your notes. Sorry, guys. So we got that output over the input, generally speaking, for the first order system was 1 over tau s plus 1, right? And when it comes to the unity feedback block diagram, and I told you that here you have to put the G open loop transfer function is 1 over tau s we found from here, and this is the output, input, and being compared with that, and this is the error signal. Today I'm going to go to the Simulink, okay? Okay. So, and we applied, if you remember, x of t as the impulse, x of s as the impulse, which is 1 in the Laplace transform. And we saw that if we apply the, this is the input to the system, impulse, and you saw that the output follows the input. Yeah, we did it with mathematics, that's right. Here we go. Here we go, output, and here was 1 over tau. Second, I applied unity step, 1 over s, and you saw that we derived together that if this is the unit step, is the input to the system, here is 1. I showed you that this is the output follows the input. Okay, for both of these two, we saw that the steady state error signal is 0 because the output, steady state output follows the input, right? So this E, or E when time goes to infinity, a large value is 0. Because we define E as output minus input, right? From where? From this block diagram. Let me show you. I taught you in the previous class from here. E is, sorry, input minus output. This is the sign mistake. Minus input minus output for unity feedback. And then I apply input as the ramp, 1 over s squared, and I showed you that if you plot this mathematically, we derive together if this is the input, you have a steady state error signal. It was like this. Here we go, constant. Here was the error signal, right? See? And the steady state error signal we derived together was tau. You got it? But also I told you, we stopped here, that ESS from final value theory that I told you was the limit of S, x of S, you have in your notes, 1 plus G. To validate this, when S goes to 0. So limit of S, x of S is for the ramp, is 1 over S squared, divided 1 plus 1 over tau. This with this goes to New York, 1 over S gonna be limit of 1, limit of 1, S goes down, S plus tau, sorry guys, 1 over tau. When S goes to 0, this is 0, tau goes up, tau. Here we go. Even you can implement this for the this and this, and you get the ESSs here. Please do it as homework for yourself at home. Okay, you got it, everyone? It's been recorded, hopefully. Yeah. Can I go to the next page? Yes. So, and now the fourth case is when the x of s is the parabolic, means 1 over s cubed. I taught you this, right? Parabolic. So from here you get y is equal to 1 over s cubed tau s plus 1. We are talking about the first order systems, guys. We put here and we're gonna have that. So you can write this as a over s cubed, s cubed plus b over s squared. This is very elementary method. S plus d over tau s plus 1. And you can write this simply as s cubed tau s plus 1. And now it's going to be a tau s plus 1 plus bs tau s plus 1 plus cs squared tau s plus 1 plus ds cubed. That's right. Numerators, they are equal. So this numerator is gonna equal to 1. So if you write here and you're gonna have s cubed is this c tau plus d. Now s squared is b tau plus c. That's right. And you have s is a tau plus b, yeah, and the only constant number here is a from here equals to 1. Right? Because I'm double checking with you, let me double check. This is d and this is c tau and this is square. This is b tau plus c, b tau plus c, and s is a tau plus b. So from here you get a is 1, obviously. If you implement here, you get, sorry guys, you get, I'm very sick. You get b gonna be minus tau, and if you put this here, you're gonna get c gonna be tau squared, and if you put this here, you're gonna get d gonna be minus tau cube. So being said, just replacing there, you get y in the s domain equals to 1 over s cubed minus tau over s squared plus tau squared over s minus tau cube over tau s plus 1. And you know that, as we did in the previous cases, I can rewrite this. I can remove one of these from here. I'm going to say square, and this is going to be 1 over tau. Clear, everybody? Yes? So, how to find time? How to find that? Tell me, you tell me. Find time, gonna be Laplace inverse. So y of t, or so this is input, obviously, this one. input parabolic. This is minus tau t ramp 1 over s squared. This is unit step tau squared unit step 1 over s, and this is our decaying term tau squared e minus t over tau. Bingo. Here we go. Okay, everybody? So, you tell me, what was the name of this? The last term? What was the name of that? Yes, so it goes to 0 eventually. And we define error signal as input minus output. Input is this, output is this. So it's going to be 1 over 2t squared minus y. From here, it's going to be tau t minus tau squared because unit step is 1. That's it. This is your error signal. And interesting to see from high school, when t goes to infinity, error signal goes to where again? T goes to infinity, error signal goes to infinity. You have increasing error signal, guys, in this system, with the input of what? Parabolic. Being said, if I want to plot it, I know I'm going to go to MATLAB and Simulink eventually. So if this is y, this is t. If this is the input to the system, parabolic, you're going to have this, the output, going to be this. See? Is error signal increasing with time? This is error signal. This is output. This is input. Understand, everyone? So it's validation very easy. Can I go to the next page? Yes, guys? Validation is very easy. Final value theorem. ESS is the limit of S, again, x of s over 1 plus g when s goes to 0, as we did for the ramp. So it is 1 over s cubed because this is parabolic. 1 plus 1 over tau s when s goes to 0. If you put everything there, it's going to be 1 over s squared plus s over tau when s goes to 0. 1 over 0, infinity, large number. So you see that ESS goes to increasing. So you can make a table here. Actually, I'm going to extend the table after second order systems. Okay, but for now, you can make a table. Here is ESS. This is the first order systems. And this is the impulse as input, step as input, unit step, ramp, and parabolic. We saw that for the impulse input first order system, I'm writing here y over x closed loop transfer function is over 1 tau s plus 1 for this system. So it is 0, we saw that. This is tau constant error signal, and here is infinity. And you are here as mechanical engineers and the future control engineers to design controller to make this error steady error signal to 0. These are not good. These are not good. You have to make that 0 by PID controller or read lag controller, whatever it is. Okay, these are not good. Your function is this. You got it? Yes, guys? So guys, I'm just giving you a heads up for next month, but from now, because I'm in the first order system, so when I teach you PID controller, you saw that for the step input, this was the step input, unit step input, we had this profile, and we know that the error signal is 0. You had this profile. Here we go. Okay, output follows the input. When I will teach you PID controller or lead lag controller, actually mainly PID controller. One of the methods to tune the gain of the controller is that we have to say if behavior of any system, second order, third order, 10th order, is like as you're gonna hear from me, delayed first order system. Its response, its step response, let me write clearly for you. Its step response, this is step responses, right? Response is delayed first order system. So this is first order system. When I say delayed, means this, means it's starting from here. You have a delay here, nothing happens, this delay, say T naught. And I taught you that a Laplace of, you have your notes, f of t minus t naught means delay is e minus st naught f of s. Remember, you have your notes? And we did too many things in Simulink and in mathematics. So this gonna be like that. I'm gonna teach you to design PID controller. E minus, say, tau s or tau s plus 1. This is the transfer function of this green line because this is delayed, this delay. Just giving you a heads up from now. When I say delayed first order system, is this. Because you're in the first order system now. Oh man, it's very hard to teach by COVID. Okay. Okay, you got it? Now, let me go and to Simulink and rapidly and share with you and visualize what we have done. And then I'm gonna back to the fifth input to the system, which is a harmonic input. Based on that, I'm gonna teach you the Bode diagram. Okay, then I'm gonna teach you that what is low pass filter, high pass filter, and these kind of things. It's very, very funny things. Okay, so MATLAB. For example, when I'm going to Simulink, guys, I'm going to say that the tau, just a number, huh? I'm going to say tau, just a number. Time constant is 2 seconds. 2 seconds. So because we cannot go with Simulink and MATLAB. So on the other hand, your closed loop transfer function gonna be 1 over 2s plus 1. And obviously, open loop transfer function that we're gonna put in the Simulink gonna be 1 over 2s. You got it? Like this one. What is that? Here we go. 1 over 2s. Okay, you know what I'm gonna do? I'm gonna open the previous class Simulink file. Yeah, here we go. Like which we're at yeah, modify. When you click on that, the preview of the Simulink emerges here, guys. You're going to use this as a control engineer. You're going to use this in real-time toolbox of MATLAB, and you can connect this to your real device. Okay. Open model. When I was using MATLAB Simulink, it was 2000. How many years ago? 24 years ago. It was a very trivial version of that. I was an undergraduate student in Iran, so let's see. It's coming up. Yeah. Come on. Okay. So what I'm gonna do, I'm gonna come on. Okay. I'm gonna select all work, Control A. Okay, Control A. Control C, I'm gonna copy and paste here. I'm gonna share with you after the class. I'm gonna Control V, just putting here. And then I'm gonna save it as first order systems. Okay. Oh, okay. Whatever. First order system. Not a valid model name because it's a valid. Oh! Oh, maybe not number 1. First order. Okay. So, okay. And then I taught you that we don't have impulse in MATLAB, so we want to put the derivative. I'm removing the delay because I don't want to teach you the delay anymore. Okay. Okay. I don't need these, none of these, only this. And I have to change this because it's a first order system. You're gonna change the numerator and denominator is 1, so gonna be 0s plus 1. And here is tau s plus 1. So here is 1. Tau, I said, is 2. See, 2. 2s plus 1, that's right. But this is a closed-loop transfer function. We have to put the open-loop transfer function. 1 over tau s. So here is 0. There we go. This is our, see? 1 over 2s, as I said here. G open-loop transfer function. So I'm gonna copy this. Actually, I can copy this and put it here. Here we go. The same. This is and now I'm gonna do the same. Delete. Control V. Right. Oh my God. Okay. And I have to play with this, so I'm gonna assign as a homework with you. Okay. Because you have to change 2 other things here. Yeah, I'm gonna assign as a homework. I don't want to waste your time with this. This is enough. So actually, I'm going to show by MATLAB coding on that part. So you see that Oh, here probably we're gonna have delay, right? Step time, no. 0, final value 1, and here we have delay also. I have to fix this. So start time 0, slope 1, ramp, and let me double check this. Step time 0. Okay, so if I control C this, and so you see this is the uh, this is the impulse response for the first order system with the time constant of 2. Here we go. This is the output. Sorry, this is the input. This is the output. See, the final output follows the input. See what I'm saying, everybody? And this is unit step. The blue line is the input. The red line, as we plotted mathematically to be derived, is the output. So the output follows the input. If you increase the time a little bit, you can see that 15 seconds. Okay, here we go. Here we go. See, output follows the input. So error signal is 0, and this is ramp. See, this is the input as we plotted. This is the output. We have constant. See, constant. What? Constant error signal. And if I show the error signal of this, you see, error signal is starting from 0. You have a constant finally 2 units. Constant error signal. But here's error signal based on the table is 0 finally. See, starting and goes to 0 finally. Steady state error signal goes to 0. And here also for the impulse, see, starting from this and finally goes to 0. From 10 and finally goes to 0. Error signal. So you have to design a controller put here before this to fix that. You get it? Huh? So just showing you again. I'm not teaching you. Okay, just showing you if I put PID. Okay, PID controller. Just showing you, emphasizing. I'm going to teach you later. And put this here, and only I'm going to use I controller. I'm going to teach you why later. Let's say, I don't know, 2. I controller. So if I want this, maybe PID, but oh yeah, so PID. P is 1, and actually let me put PID. Okay. Here we go. Finally goes to 0. As in this underdamped that I made system underdamped, and finally goes to 0. If I increase that, these are just random numbers I'm giving. Okay. This is a method to tune those PID things. See, finally emerges to it. Okay, so error signal, and I make the error signal finally. Let me increase the time to, I don't know, 60. See, error signal goes to 0 finally. So I fixed the problem by controlling. And this is, I made the system underdamped. I'm going to teach you in a second order system. You can make this much smooth than this, okay? By what? By doing this. So yes, derivative, I don't know, put as 4. If I do this on 60 degree, here we go. See, it's very smooth. And look at this. The signal goes to 0. Respect to amplitude. Okay, forget about that. So, and you know that how to code in MATLAB. Let me just teach you coding. I know that num equal to 0 and 1. In MATLAB coding, you have to put the closed loop transfer function. In Simulink, open loop, I'm emphasizing. 2 and 1, this is not closed loop transfer function. Okay, guys, understand? I'm emphasizing. Remember, for coding, you have to put closed loop transfer function, but for the Simulink, you have to put open loop transfer function. So if say step function of num and then, here we go. It shows the same result of the Simulink. Here we go. Step response. All step response. Remember, if I added a derivative to make it to impulse, remember that we were doing previously. So you're gonna have 1 and 0. Then is the same. I added derivative, right? I shared code with you. This must be impulse. See, exactly showing the impulse response. Remember that we were doing together, guys, the other day? Okay. This 1 means S. This 1 here means S. We added derivative. That's right. So this is what we have here. Okay. Now let's go back. I'm gonna share the Simulink code with you. Yes, after the class. Let's go back to the notes. Oh no, please. Okay. So, new slide. Okay. Now, as I promised you, we have the fifth input. When x of s is omega s squared plus omega s squared. It means that your input in time domain is harmonic sine omega t. Okay, before going ahead, guys, why I'm doing that? Because I have to teach mathematics. Because this input, we name it as frequency response. In the vibration, I was teaching that in another style, but this is control. Frequency response means input to the system is harmonic. Okay, means that the input to the system y t is harmonic like this, and we want output exactly follows this, like as a rotor that is rotating in industry machinery. Okay, or engine of the airplane. Okay, also we want the output follows kind of like this, output be like this. If your output is not like that, output is like this. Look at here. So you have a phase difference between them and amplitude difference between them. Okay. At the end of the semester, when you see that, we name it as phase margin. Phase, these are technical names. Phase margin at the end of the semester, and gain margin. Gain margin. When your output doesn't follow input for the harmonic, so you have phase lag or not exactly the same amplitude. So by using the controller, we're gonna fix this. But now this frequency response leads you that I teach you how to go the body plot of different systems. Here first order system and later any order system. Okay. Body plot. Body plot means you increase frequency, excitation frequency, from 0 to a large number. I don't know, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5 radian per second. Okay, frequency, and see how the output behaves with respect to the input. Simply speaking, body plot is like that. Okay, but before plotting you mathematically, I have to teach you some elementary math from high school, from university level, refreshing it. If you have a complex number like this, a plus bi divided by c plus di, absolute value of this, for refreshing your mind, is this: a square plus b square divided by c square plus d square. Very, very simple writing in the level of kindergarten. And the phase of number a is arctangent or tangent inverse of b over a minus arctangent or tangent inverse of d over c. You got it? Yes, everybody? These are trivial mathematics. So now you're dealing with the first order systems. Tau s plus 1 closed loop transfer function. Remember when I was teaching you control, when we went to the Laplace transfer, I told you what is S. Look at your notes, you tell me. What is S? What is S? I defined to you. Look at your notes and tell me. What was the S? S was I omega or J omega, remember? Yes, everybody? And this was frequency characteristic. Frequency characteristic. Yes, guys? So y over x is 1 over, I'm just replacing s as it is, tau I omega plus 1, or tau omega I plus 1. Now you see I generated a complex number. So in Bode plot, we're going to plot this 20 logarithm log of absolute value of output over input, closed loop transfer function. You have to plot this for the amplitude. This is for amplitude. Okay, and then we have to plot just below that phase angle of y over x closed loop transfer function. By doing this, eventually today I'm going to show you that the RC circuit that I was teaching you is low pass filter, and you're going to have lots of fun. By plotting this, I'm going to show this is low pass filter. Maybe you heard that. Low pass filter. Okay, guys, everybody. Can I go to the next page? Yes, I'm going to teach you by hand first, but we have a very simple command in MATLAB to plot the body by coding. Very simple, two lines, even one line. Okay, so let's go. Next page. So 20 logarithm of y over x, and if I say the amplitude, when its unit is decibel. Maybe you heard that in the sound, 2 decibel, 3 decibel in your audio system in your home. Okay, so it's going to be 20 logarithm of 1 over tau omega square plus 1. Here we go. Exactly based on whatever I did here. This is 1, so tau omega square plus 1. Okay, let me plot this for you guys. You see, still I'm playing with the high school what? High school math. A in decibel, and here is frequency omega. I'm gonna say part A. If I assume that the frequency, excitation frequency as input is much smaller than 1 over tau. So this tau over omega gonna be much smaller than 1, this one. So you can ignore it. You can say, okay, bye-bye. I mean this area. Very small value of omega, excitation frequency. So A gonna be 20 logarithm of 1 over 1. What is log of 1 from high school? What is log of 1? 0. Here we go. So I say here is 1 over tau. 1 over tau. So here the amplitude is 0. When I say amplitude 0 means y over x is 1. Understand me, guys. Y over x is absolute value is 1. Means output follows the input, is exactly as input. See what I'm saying? Understand? So simply speaking, if this is your input for first order and for first order system and low frequency, output gonna exactly have the same value. Here we go. And we plot like this here, like that. Here we go, 1 over tau. B, if omega equals to 1 over tau, this point, at this point, okay? If that's the case, just again, let's go back to elementary school. Your A gonna be 20 log of 1 over tau in tau 1. 1 plus 1 is root square of 2. You can use that, but I remember it is gonna be almost minus 3 decibel, minus 3. Here, so suppose that here is minus 3. So this is gonna be, guys, let me plot change. This is gonna be like this, guys. See, here we go. Okay. C. Suppose that your excitation frequency is much lower than higher than 1 over tau. By saying that tau omega is much higher than 1. Okay, so you can say A is equal to 20 log of 1 over tau omega. For example, I'm giving an example, okay? I'm saying omega is 100 tau. 100 over tau. Sorry, guys. 100 over tau. So this is going to be 20 log of 1 over 100. You know, this is going to be minus what? Minus what? Let me give you first this because I want to play with that a little. First 10 tau. If 10 tau, this is going to be 10. Oh, this is going to be 10. The result going to be how much from high school? Minus 10 decibel. So you see that 10 tau, say, you're writing like this. 10 to the power of 0 over tau. I'm going to show in the MATLAB. So it's going to be here, going to be minus 10. Say here, a straight line. Okay. Now, the next case, I'm giving you omega is, as I told you, 100 tau. 100 over tau. So you say A gonna be 20 log of 1 over 100. This is gonna be minus 40. See, it's linearly. Oh, this is, yeah, minus 40. Is this right? Yeah, minus 40. So this is like that. There we go. Okay. And here is suppose that is minus 20. Minus 40, I'm sorry. Minus 40. Okay. We plotted the body plot right now together. Guys, this was for what? First order systems or RC circuit. Remember, we were talking about the RC circuit or spring and damper or the tank of the water. It's interesting. It says, listen to me very carefully, guys. It says, when the excitation frequency is very low value, output follows the input here. The name of this frequency has a name. It's cutoff frequency. Cut-off frequency. But for the first order systems, if you increase the excitation frequency, output gonna lower than input. Look at here, guys. If I increase the frequency, it's gonna be this. This is for high frequency. Interesting, right? And the guys that had vibration with me, we had another version of this. Okay? So why you say low pass filter? This is low pass filter. Because only low frequency are being passed. Output follows the input. For high frequency, the output diminishes, reduces. So only passing low frequency. Low frequency. For high frequency, amplitude decreasing. The output is decreasing. You got it, guys? Yes, everybody? Yes, guys? Huh?
Yes.
Good. So, if I go to Simulink, I'm gonna back to this for phase. Just I'm gonna show the powerfulness of the MATLAB. I'm not done yet. So you see that, guys, you see that stable RC circuit, spring and damper, tank of water with a stable pole at the left-hand side. When you have the input, harmonic input, they are low pass filter. When you go to industry, they're gonna say, okay, we need a low pass filter. We need that. We're gonna remove high frequency response from the system, simply like that. We don't want to have high frequency response in the system. We want to only keep the low frequency response in the system. Clear, everybody? Yes? So for, say, num is 0 and 1, first order system, it is simple like this. Then is, again, tau is 2 and 1. Again, for the body, you have to use closed loop transfer function. As we analyze, look at here, closed loop transfer function. See, closed loop transfer function. Okay? So, body, as I write, num and then, here we go. You type, MATLAB comes up. Here we go, as we plotted, guys. This is for this is your this is -3. You have to find it. This is your cutoff frequency here, and then linearly decreases. So this is low pass filter. This is magnitude or amplitude in decibel. This is phase, coming from 0 to -90. I'm gonna do it mathematically now. Okay. So this is low pass filter body diagram. When that happens, when the output, you have first order system, this is for that. Okay. Now, Let me visualize this for you guys, this plot. See, I said if you have low frequency, output follows input for first order system. If you have high frequency, as plot shows, output doesn't follow, you have decreasing. Let me take you back to our lovely simulink. And I'm gonna first order I'm sharing with you. Okay. Open the model. Okay, because I'm going to share today this with you. Okay, let me do this. Control C. I'm going to move this here. This is the first order, so nothing changes, except now the input to the system is sine. Here we go. I'm going to put sine here. Okay. And a cosine, sine. Oh, sine wave function. Why it's like that? Sine wave. Okay. Here we go. Sine wave. So input is sine wave. Let me make this big. Here we go. Desirable input is sine. Double click on that. Amplitude is say 1. Frequency, I'm gonna say 0.5. Very low frequency, radian per second. Do you see that, guys? Everybody? Yes? And no phase. We don't have no phase, okay? Here we go. If I do this, low frequency, this is input, output. Let me put this at 20. I'm going to examine first the frequency. Oh, this is high for this. Let me put around frequency of 0.05 or 0.1. Good. So let me put this as 60 again. I made frequency very low. See, 0.1 radian per second. So if I run this, you see the amplitude almost the same amplitude. Okay. Let me put this 250. I want to just make sure to. Here we go. Almost amplitude, almost. If I make the frequency lower, it's gonna be very close together. Okay. Output follows the input. Let me make it lower here. Let me put this as 0.05 radian per second for this first order system. This is depends on tau. This 2. Here we go. Okay, almost the same. Now, if I increase the frequency to 0.8, even higher than that, 2. Okay. Oh my God. See, the yellow line is output and the blue line is the input. See that the amplitude decreased significantly. This is both the plot that we're visualizing. For high frequency, decreased a lot. See what I'm saying? 2 log of y over x. You got it, guys? Yes, everybody? Yeah? And this is not good. So you have to design a controller for a high frequency, if you, for example, to fix this. But this is low pass filter. So you see that the first order is by high frequency, the amplitude decreases. for high frequency. For low frequency, amplitudes are the same. You saw the effect, everybody? Yes? So like, as I said, 0.1. This is low frequency. Here we go. See, they are exactly close, kind of. So I increase the time to 750, either 800, because I decrease, I need more input. See? Output exactly follows the input. So for high frequency, you saw that there is a huge gap, gain margin. We have to fix that by designing controller toward the end of the semester. Also, they have the phase margin. Their phase for high frequency, they are not the same. You have to fix it by putting controller here. That's the story of body plot. Yes, save it. Okay. And I'm going to stop it here. The phase one, I'm going to plot the phase one mathematically in next class. And then I'm going to teach you high pass filter. It's interesting, you know that, guys. The same first order system, if I change the place of C and R and get the voltage of resistor, it's going to be high pass filter. I'm going to show it mathematically and by body plot and control. And then we're going to move to second order systems. Hold on.